So on the schedule this morning, this is finishing up the quality section of the course. We'll have a review next Tuesday where I will go through all of the answers and everything of the homework and answer your questions on the other homeworks and help you prepare. So study those homeworks to get ready for the exam. I'll be taking, a few problems from each homework, changing the words, changing the numbers, kind of modifying them a little bit. You kind of know how I do things from PCHEM 1 if you had me for PCHEM 1. There's a few people that may not have had me for PCHEM 1. And, I need to remember to bring the bumper stickers. So you guys wouldn't be in here if you didn't pass PCHEM 1, so we need to get the bumper stickers, honk if you pass PCHEM, and I need to bring those. And so anyway, it's great. I love to see them around town. I always honk. So don't get mad and flip me off. It's the bumper sticker. That's why. Yeah, I haven't been flipped off yet, but I always worry about that. So we'll go through advanced statistical tools, and then I think there's some fun things in today's lecture, so hopefully you enjoy it. So this is, we're trying to get what's called the totality of circumstances. You see that here down at the bottom. We're not just looking at the chemical signals that we get out of an FTIR. Okay, that's important, but occasionally chemists have been caught in an embarrassing situation. Like if you take say a carpet fiber and you run it on an FTIR, you squeeze it on the little ATR and get a spectrum of it. It's probably going to give you the molecular signature for polyester, polyester fiber. And then you take that was a red fiber, and then you have a yellow fiber, carpet fiber, and you run that, and it gives you the exact same FTIR. Why? Well, because the coloration is such a small concentration in that polymer, you're just getting the FTIR spectrum of the polymer. So if you neglect color or texture, that's important information. It's not a number, though. It's not something that you get. Color is. That's why we did the RGB lab. But, it's orange and yellow are totally different, but you might not pick it up in an FTIR. Okay. So you'd want to do a UV vis, maybe get a spectrum of that, a visible spectrum, reflectance spectrum on those. But still, granularity, texture, number of samples, origins of samples, all of this is information that builds out what we call the totality of circumstances. And so you really want to match things. We're really in forensic science doing the art of comparison. So we're trying to compare as many features as possible. And if the features don't match, that's exclusionary. We're like, this is not the same as that. And that's important too. So it's not just matching to make things, to say this is the same as that, but it's also we want to necessarily exclude things too. So here we do this for incoming evidence. And so here's a subdivision of incoming evidence. If you look at all those bags of ecstasy pills, that's a lot of pills. What do you see? I see some greenish yellow ones, and I see some bluish ones, light blue. It's kind of hard with the projector. They're a little bit more vivid on my screen. But up here, these on the back side, at least that one and those three look more blue. And maybe with the lighting, that would be blue too. But then right here, it starts to look almost green. And these up front look kind of green. So we would separate those because they're different colors. Now, we might do the chemical analysis and they have exactly the same chemical fingerprint, but they're definitely different colors. And so we would say, well, there's different seizures. This would also help us figure out how many to sample. Same thing down here. We have all of these vials and droppers and everything like that for injectables. We have all of these. Look at all those guys. So we would add all of those up. We would pick 20 of them, and then whatever's left after 20, we would take how much of the rest? What? Yeah, it's the first 20 and then something percent of the rest. Yeah, 10% of the rest. And then looking at this, it's like this whole bag is almost the same, but then look at this one. Those are all clear, and this one's not clear. So this one does not belong in that group. It's kind of like Sesame Street. Which one of these does not like the other? And so they've got the little song. All of these look the same. They have white lids. These have red lids. So we're going to treat those as separate seizures. And this one has amber bottles, okay? And then more droppers with clear liquid. These might be the same as those, but they weren't in the same little bag or bin. So maybe there's something different. So we don't want to mix our seizures. We want to break this up and subdivide. That's more work for the lab. You know, it would be much better if we could include all of these in one, like this is this case, these are all the same sample, but they're not, you know. So we need to break them out. We're going to be taking 20 of each of these little things, and then if they're over 20, then we'll do 10% of the rest, and then set that up as our lab samples. And so in this whole scheme today, we're going to pretend we've got 3 seizures of cocaine labeled A, B, and C. This is one of the examples in the book. We don't know necessarily, we're not told in the book example what separates A, B, and C. Maybe it's a different colored bag or something like that. But anyway, something in this large seizure of 30 packs, we've divided it into groups of 10 for some identifiable reason. Okay. And so what we want to look at is, are there patterns or groups within these 3 seizures? And answer the question, are they all the same? So these are some of the questions that we'll be asking. Are they the same? Are they related in some way? Is there some, maybe they're from the same source, or maybe the same prep method or something like that. And so we're going to be looking at their multiple ingredients in these packets, and then we're going to be using advanced statistical tools to kind of pull out information. Now we're going to do a lot of tools on this same data set, but it's not necessarily, you wouldn't do all of these on the data set. You would do the tools that make the most sense. I'm just trying to show you a broad range of tools that you could use. So this is the data that was in the table in the book, and I put it into Minitab. I also put it into Excel, and you'll see. But the first thing to do is we can sort of look to see, the nature of the data. These are the percentages of cocaine, procaine, and caffeine. And then this is the case ID. So in group A, we had 1, 2, 3, up to 10, and then group B, 1 through 10, and group C, 1 through 10. Now this looks reasonable. You might type your data in like this, but I would say there's a problem with this data. Okay. At least with the labeling of the data. There's no way for a computer to identify all the A's because the numbers are in there too. So we want to break the number away from the letter so that the computer can say, oh, all of these rows are labeled A. So they're from the same group. Right now, the computer looks at this and knows that it thinks that A8 and A9 are totally different. We need the computer to be able to group or block the data. So that's the first skill I want to teach you. That is blocking the data correctly or logically. So it sounds like the word blocking could mean, to block something, but it also means like to group. So that's the way we're using this. We're grouping the data in A, B, and C groups. So look what we've done. We've taken that case ID column and split it into a column that's the different group, the seizure group, A, B, and C, and then the individual sample or pack inside that group. This column is really not necessarily that important, but we'll still identify it by this column. But this is the most important one that we're doing. We're making sure that the computer can look at this and say, okay, let's group by A and get a mean for A, a standard deviation for A, a range, all of those statistics for group A and group B and group C. It could not do that with this column. Now maybe you could do it in R. Maybe you could program it to take just the first letter of this thing. Yeah, you could probably force it to do that, but I find it easy just to break it into 2 columns. And so this blocking is another way to say grouping. That's all. And so we can plot this. Now Excel, I've been using Excel since believe it or not. Let's see, 19. I entered graduate school in 92, and we were using Quattro Pro. You've never heard of that, I'm sure. Quattro Pro. It was part of the WordPerfect, Lotus, Quattro Pro. It was a different Office suite that Microsoft was going to compete against. So then Microsoft came up with Microsoft Office and just obliterated all the competition. And then we switched over to Excel. So that was in probably 93. Yeah, 94. So I've been using Excel that long, and Excel still has not added the 3D scatter plot. Okay, it's pathetic. How hard is that? 3D scatter plot, and they never have. They've got like a surface plot that's 3D, but they've never added the individual dots, the little drop lines and everything. So, you don't have the option to do this in Excel, but you can do it in Minitab. You can do it in I'm sure R or other stat packages. But that's one way to do it. We've got 3 different compositions. We have caffeine, procaine, and cocaine. Let's just plot X, Y, Z for all 3 and see what we see. And so this is the way you do the scatter plot. And in Minitab, you have the menu command graph, 3D scatter plot. You say with groups, and now it knows, okay, I've got groups in here, and you tell it which the grouping variable. Here's the category grouping variable, seizure, okay? And it's going to grab those, and it's going to give us A, B, and C as our groups, and it's going to color code them. And then it's going to plot as the Z variable, caffeine, procaine, and cocaine as X and Y. And here we have it. And so immediately we can see there's something unique about group A. Does everybody see that? Group A is over by itself, and group B and C are all mixed together. So something's different about group A. Instant, we know that. Now we're going to get that same conclusion over and over again using all the different tools. So that's a handy thing. Any questions on the scatter plot? There's one other piece of information you might be able to draw out of this, and that is that there's a negative correlation between cocaine and procaine. So over here on the low side of procaine, between like 10 and 15, we have all of the high cocaine samples. Okay, and then on the high side of procaine, we have all the low cocaine samples. And so that red line is kind of the slope or interaction between cocaine and procaine. And so when this goes up, this goes down. And so there's a negative correlation between cocaine and procaine. We will get that same conclusion from other charts and even from the correlation tool, but you can see it here in the scatter plot. Okay, let's look at the box and whiskers plot. So here's a box plot in Minitab, graph box plot. You can do it with groups. So it categorizes by the seizure column here, A, B, and C. My laser pointer just died. Oh, there it is, seizure. And then we can have the graph variables, cocaine, procaine, and caffeine. And so here's our box and whiskers plot. It has group A here. Let me just do this with the pen. So it does group A here and then group B here. You see where the A and B and C is sort of out a ways, and it's showing you the groupings of those. So this is the dividing line between the different groups. Okay. So tell me what conclusions you guys see. Let's start at the bigger picture. Compare A, B, and C. Yes, A clearly has more cocaine than B and C, so that makes it unique. You could also just look at the pattern. Look at the patterns of B and C. Small, big, small, small, big, small. So this has this kind of pattern between their medians. Okay. So you see the same kind of pattern there, and here you see this pattern. So you can say, okay, we've got a different pattern on B and C. Those look similar, and A looks different. So A is unique. That's a good one. Yeah. And you can see over here as the cocaine goes down here, the procaine went up, and the cocaine went down here, and the procaine went up compared to this spot right there. Yeah. There's a significant difference. How do I know that the difference in cocaine is significant? Because here's the little range. That's like the smallest value of cocaine in seizure A, and this is the maximum value of cocaine in seizure B and the maximum value of cocaine in seizure C. They don't even overlap. So when the box and whiskers don't even overlap, you've got two different populations. If they're overlapping a little bit, they might not pass the t-test. Like the t-test would say they're probably the same population, but when they're not even overlapping, the t-test would say there's this from different populations. So the null hypothesis would fail if the boxes don't overlap. But if the boxes do overlap, the null hypothesis you would fail to reject the null hypothesis because they're probably just statistical variation in the two samples would probably be wide enough that you wouldn't be able to say they were significantly different. And look at the caffeine ones. That's an example. Like, it's probably the same. You couldn't say that these were different amounts, right? The t-test would you would fail to reject the hypothesis that you would fail to reject the hypothesis that the caffeine was the same in all three seizures. So that's good. Looks like A is different than B and C. Okay, you can do box and whiskers plots in Excel now. So they've added these. So that's great. You don't have to, for a box and whisker plot, you don't have to go and buy Minitab. Now, I know this isn't in your notes, but I wanted to just sort of get some screenshots for you for Excel. So you have this in the video. You've got your data. You can select your data, and then up here under the different charts. So we're on the Insert tab here, and then this is the Charts area. You pick this chart that looks like a histogram. Just do the down arrow, and you've got the histograms here, and then you got the box and whiskers plot. So you click on that guy and pop. There's the chart. So let's zoom in on the chart. It's the same chart, so that's cool. I always like it when Minitab and Excel tell me the same thing. Okay, and you can see it. These are the default colors. You can go in there and edit it. Although these new charts are a little weird, you can't. I wasn't able to edit them. I was trying to make the box bigger and some other things and move the legend. And I think it's created with some sort of macro in the background of Excel, and so the ability to edit it and make it just the way I wanted it was somewhat limited. So if you experience that, you're not doing anything wrong. It's something with the chart. Same conclusions though. I like this because it's color coded. Okay, let's look at this one. This is a crazy plot. This is called a matrix plot of correlations, or an interaction plot. I could put that also known as, or AKA. So what we're looking at is how every data type interacts with every other data type. So if you look at here, it's a 9x9 square because we have 3 data sets. We have 3 sets of numbers: cocaine, procaine, and caffeine. And so these ones down the diagonal is the cocaine data plotted versus the cocaine data. All right, so it's a slope of 1, right? So that's why it's all right here. So for this data point, for the data point that had 20% cocaine, we come across, and guess what? It's plotted on 20% cocaine. So you think, well, what possible value could that have? Well, it does show that the group A is totally different than group B and C in terms of the amount of cocaine. So that's even what seems like a silly plot. It's just saying, yeah, A is totally separate than B and C. We see here that negative correlation. You see there's kind of a negative slope there. So the high cocaine values have small procaine values, right? So here's the small end of the procaine, and then the high procaine values have the small end of the cocaine values. There's really not much else to say. Here's the caffeine, procaine by caffeine. You see it's kind of just a mishmash here. There really doesn't seem much correlation there. Okay, A and B and C are different. Negative correlation between procaine and caffeine. Okay, so let's look at the correlation matrix. If we have this correlation, which we can determine graphically, right? But what is the slope of that line? Like, how strong is the correlation? If it's a really strong correlation, let's say I go 1% change in this variable, and it creates a 2% change in that variable because the slope is 2, right? So if you know the slopes, you know how strong the correlation is. If you don't know the slopes, then you can just say they're correlated. Also, the data is kind of scattered. So what's the p-value for that correlation? It'd be nice to know. Is the correlation statistically significant, or is it just kind of look significant? So that's what the correlation matrix will give us. So this, you go to basic statistics correlation and display p-values. And then if you're going to use a p-value, you need to know what the null hypothesis is. So it's no correlation. That's the null hypothesis. And then the p-value is the probability that there's no correlation. So after you do this, you don't see any graph. This doesn't give you a graph. It gives you a little table in the session log. So you go to the session log. Here's how you do the correlation thing. You get this dialog box, put in all three variables, display p-values, and here's your matrix that you get. And so this is the triangular matrix. It's just the bottom three of this graph here. It's just these three, because they're the same information as those three, and the diagonal really doesn't tell you anything because it's the variable times itself. Okay, so it's just these bottom three right here, and that's what you get right here. So we have the cocaine-procaine correlation, and it's negative, which is what we saw. When cocaine goes up, procaine goes down, and vice versa. And it's 0.5 cocaine for procaine. So, and then this is saying there's one between cocaine and caffeine, which we didn't really identify. And this is saying there's a really small one, 0.04 of procaine and caffeine. So those are our three correlations. But let's look at the p-values. This one is statistically significant. Yay. Okay, this one is surprisingly, we didn't see that, but it's statistically significant. It's really small, and it's a positive correlation. So when cocaine goes up, so does caffeine by half. Okay, but then look at this p-value. Not much, right? Not it's 0.83. So 84% chance that one's just done by variability in the data. So the null hypothesis has an 84% chance of being true. No correlation. So even though we can calculate the correlation between procaine and caffeine, we're saying that's not statistically significant. Okay, so that's the conclusion that we would get. But the first two are statistically significant. And so this is what we saw in the chart. As cocaine went down, procaine went up. But it's so tiny, but you can see that, yeah, caffeine did go down. It was here, and it went down, surprisingly, a statistically significant amount. So cocaine went down, and so did the caffeine. So they're both going in the same direction, which means they have a positive correlation. That means they're going in the same direction, either down together or up together. Only when they go opposite directions would they have a negative correlation. Okay, we can do this in Excel. This isn't in your notes. I did this last night just to add a little bit, and I thought, well, let's see. Surely there's something in Excel that can calculate correlations. So data on the data ribbon, the data analysis tool pack, you have to add in. We had to do that for solver and regression tools and PChem, so you remember that, hopefully. But if you don't, go to options, add-ins, and find the analysis tool pack. When you add that into Excel, you get a new little menu item on the data ribbon. You go in there and hit data analysis, and you get this dialog box. And of course, if you scroll down, you get the regression tool, but we're looking at the correlation tool right here. So we hit that, hit OK, we get this dialog box. You select the range of all your data. Tell it it's in columns. It's good to put the first row as labels, so go ahead and select the labels too. And then I put it on a new worksheet. So it creates a new worksheet called correlation. And the Minitab results, just for your reminder, is this. And here's the Excel results. And that's great, they match. The negative 0.520, which is what we would get if we rounded that here. The positive 0.500, which is what we would get if we rounded that one. And the 0.040 is what we would get here. Okay, so that's great, they match. However, what's wrong? Yeah, why? Excel, why? We have these correlations, which if you try to use Excel, you can print the correlations, and then we're like, oh, what's the statistical significance of those? And you're like, I don't know, Excel didn't give it to me. And then they're going to say, well, why don't you use a stat package that actually is made for statistics, and you'll be embarrassed. So don't be embarrassed. Okay. Go find a real statistical package, and then you won't be embarrassed. All right, so now let's look at how we can pull information out of these things. And this one is really helpful when you have more than 3 variables. So notice we've been able to do the XY scatter plot, which again, 3 variables, we had X, Y, and Z, so we could plot that. What if we had a 4th variable, a 4th numerical variable? We really did have a 4th variable, was the seizure, A, B, and C, so we were able to group by that. But if that variable was a numerical variable, we would have a problem. So you can't plot 4 numerical values very easily on a 3D space, right? This one can use, I mean, in theory, an infinite number of variables, numerical variables. And what it does is it clusters the data and calculates the distance between all those clusters. So in 3-dimensional space, you know, it might be, maybe this is a data point, maybe this is a data point, maybe my Coke is a data point, maybe this mouse is a data point. And so what it does is it calculates the Euclidean distance, the delta x, delta y, and delta z squared, adds them together and takes the square root. And that's the straight line distance between those 2 points in 3 dimensions. And then it can sum those, take the average value, and that's the new point that represents this cluster. So that's what's going up here. We have those 5 data points, and we calculate the pairwise distance between everything, and then we pick the smallest one. So this would be the smallest one. Those 2 points are the closest together. And so then what it does is it groups those. See, in this case, group point 2 and 3 were the closest, and so we create a cluster. And so we combine these 2, and we put a new point right there in the middle. So that new point is now the origin of that cluster. And then we recalculate all the differences. And so then the distance between this point and the center point of that cluster is calculated. And then the distance between that point and 5, the center of the cluster and 5, the center of the cluster and 4, and that point and 4. And then we pick the smallest line, the smallest distance, and make a new cluster. So we group it here. So now we have a cluster and 2 data points. And we put a new point here that represents this cluster right in the center. And then we recalculate the distance matrix. And what do you think is going to be grouped next? We have this distance. We have this distance. What's next? 4 and 5 are closer than that cluster is to either one of 4 and 5. And so we're going to group 4 and 5 together. Now we have 2 clusters right here and right here. And then we calculate the distance between them. And then we end up with just one big ball. Okay. And that's what's going on with this dendrogram. Okay. So this distance between 2 and 3 right here is this distance right here. So I'm just going to call that 1. Okay. So that's distance 1. And then we get over here. The distance between 2 and 3's center point and 1 is this distance right here. So this was 1. This is now 2. And so in the dendrogram, this is 2. Everybody see what's going on? And then we combine those. And we have this point right here. And so this 4 and 5 now, this distance here is 3. So that was this distance right here, 3, and then they were combined. And then we get to the point where distance between this cluster and that cluster is calculated right here. So this is that last one, 4. And that's plotted. These distances are all plotted on the y-axis. And then we build this little dendrogram that combines them all. You've heard of dendritic growth, maybe? Have you seen that? That's kind of like how a tree or a bush grows. The branches divide and divide and divide. And we get a lot of this. I think it was Petrokovic's lab one time was working with nitrogen dendrites to create a little oily capsule to put her drug in it, and that could be injected. So it's a fat-soluble drug that needed to go into the aqueous environment. And so you can grow like a a little koosh ball. You remember koosh balls? These little balls with lots of little um, hairs. That wasn't hairs, but it was rubber polymer. Yeah, and it's like a little oily ball. But if you put OH groups on the end, then it's water soluble. But you can put the drug inside the oily part and stick it in the body. And when this ball hits a cell membrane, then the drug can go into the cell membrane. It's pretty fascinating. But to make that chemically, the molecule, it's a macromolecule. You need something that grows lots of little breaks and fans out, and that's called dendritic growth. Well, this is a dendrogram. It's the same root word. So it starts at the top and it branches and branches and branches and branches. So that's why it's a dendrogram. It's dendritic in nature. Okay, so here's an example with our data that we just had, the cocaine, procaine, and caffeine data. Now the downside of this is we have none of the data points on here. We don't know how much caffeine, how much procaine, or how much cocaine is in any of these from the dendrogram. But this is saying which samples are most similar and which samples are most dissimilar. And that's pretty helpful, okay? So on this chart, we can look in here and say which two baggies were the closest in composition. Y'all came to that pretty good. Well, but which B and which C? Yeah, B6 and C8, they are the closest together. That's the first two data points that were clustered together. And this is how close they were. This is the distance axis. And so they were very close. If we took their difference in cocaine, procaine, and caffeine, squared those differences, added those differences, and took the square root, that would be this number right here, really close to 0. Okay, so they are almost identical, and they're in two different groups. They're in a B group and a C group. So this is really strong evidence that we have very similar compositions in the B and the C group. Okay, and then just looking at all of these, here's B's and C's all mixed together and all being joined at various distances. And then over here, look at this, A, all A10. I mean, 1 through 10 right here. And these groups have not joined with any B's at all. So this is a very strong grouping tool. It says, yeah, A is totally different than B and C without even digging through the numbers. It's just a two-dimensional plot that splits things into similarity groups. And it's just a wonderful tool. So dendrograms get my star of approval. Okay, they're great. Also, you can kind of find samples that are wonky. Which sample in this whole 30 packs is its own bird? It's the last one to join the party. B1. Yeah, right here. Look how long it goes by itself before it's ever pulled into a group. Yeah, and so you may want to pull that one out. It's really like an outlier compared to all of these others, and see just look at that one individually and say, what's up with this one? There may be some evidence there that you want to find. Okay, something unique about that. So, and then A1 is pretty bad too. A1's weird, so it doesn't join in until later. Yeah. So this is dendrograms. So yeah, that's the most unique. And then you see them joining in. I've just kind of went through all the different clusters as they were put together. Okay, and then the next one is between A5 and 9. 7, that's the B1 is weird. Okay. We'll do principal component analysis, and then we'll practice with some more dendrograms. This one is also a tool that is helpful when you have more data than you can plot. Okay. So what you're trying to do is reduce the number of data axes or factors. And typically they want to reduce it down to 2. So you can just have factor 1 and factor 2 plotted by each other. And the purpose is to spread the data out as far as possible. So this is necessary when you have data fields that are greater than 3. You can't do a scatter plot. It reduces the data space. So think about space. We're familiar with 3-dimensional space, X, Y, and Z. But you may have a 4th, a 5th, a 6th variable. And so you have a 6-dimensional space. Yeah, I know it kind of breaks your brain, but it's the data space. And so when you have 6 dimensions, maybe you want to find a linear equation that combines those. So you have 10% of variable 1 and 15% of variable 2 and 16% of variable 3, and it all adds up to 100% of all of those variables. And so you have a y value that's some combination of the 6 variables. And then you have an x value that's a different combination of those 6 variables. And then you plot y versus x, and your data is spread out a certain way. And this would be a way to pull groupings out of large data spaces. Okay. Now, these linear combination data fields are called factors. Okay. And so here's factor analysis, multivariate statistics, and Minitab. And look at the percent variation covered by the factors. And so this is what you get when I said you have that equation, x equals some linear combination of the variables and y equals some combination. These are your combinations that you get. Okay. And so for factor 1, we're taking 0.92% or 92% of cocaine value, negative 68% of the procaine value, and 66% of the caffeine value. And so that's factor 1. And factor 2 has almost none of the cocaine value, 68% of the procaine value, and 71% of the caffeine value. Now, Minitab did some matrix math to come up with those factors in order to cover 90% of the variation in the data. Okay. Now, if you notice, this is a little imbalanced. 0.58 of the variation is covered by factor 1, and 0.32 of the variation is covered by factor 2. And so there's a checkbox, rotated or not rotated. If you do the rotated loadings, these percent variables are more even. That's all I have to say. And these are different factors. And so we can look at this factor plot. Okay, here's the PCA reports. And now it's a 2-dimensional plot, and it's factor 1 and factor 2. And factor 1 is from that table. You can look at the percentages of each of the concentrations it used. And factor 2 is the certain percentages of the concentrations, and it's plotting those. And it's just showing you, again, there's something different between A and B and C. You may not be able to get this information if you had 6 variables from an XY scatter plot or a box plot or whatever, and you may need to use principal components analysis. So even though it doesn't seem to be giving us any new information, it was easy to do this analysis with the other tools. But what if it wasn't? Then maybe this would be the only thing that would draw out the difference between A and B, C. Now, I'm not a pro at PCA analysis, but there's several people in the forensics folks, on the second floor that could help you more if you had questions about this. But this is just, I know it's for reducing the data space, and I know that it's linear combinations of those variables so that you can get larger separation in your variables. Okay. So let's play around or practice with these dendrograms. Now, sometimes you can make a distance-based definition of your clusters, and that helps you decide how many groups are represented. And so in this case, what we've done is we've picked a particular distance, and we said, look, any group that's, say, greater than 6, I'll just give it the number, is going to be classified as a separate group of data. And so that's where these colorings come from. And so if we arbitrarily pick a distance in our data, say like if it's different by 20%, then we're going to put it in a different group. And then you can do the dendrogram, and all of these distances that are below 6, let's make this 20%. Let's do that, 20%. Okay. Then we're going to call them different groups. And so here, this easily divided the data into 4 groups. And we can easily identify the most unique sample. I is the most unique sample. And it's a little tricky. It looks like A and B and C and D are both in the running for being the most similar. Maybe JK. So any questions on that one?
Wouldn't E and H be unique as well?
E is pretty unique, and H. So in each group, you could identify which one is the most unique in that group too. Yeah. But I is the last, like it's the one that has by itself the longest distance before it joins anything. Yeah. And so you can just, it's so easy to just use your eye and say which stick is the longest on a single data point, and that tells you that's the most unique sample in the whole group. Yeah, and if you had defined this lower, like let's say we said 15%, then it would cut right through I. And I would be so unique it doesn't fit in any group. So it would be a group of its own. So, does that mean it's an outlier? I don't know, but you could say we've got a unique sample and then we've got 4 groups. Here's another one. So here the distance was set at 5. And so you've got 5 distinct groups. Now these are cities and states. I don't know what's being plotted here. I just grabbed it out of an example on Google. But here it's saying Iowa and New Hampshire are the closest. Okay. So I don't know what they're plotting because they're not next to each other, and I don't know what Iowa and New Hampshire have in common, but that's what you've got there. So what's the most unique?
I think it's California and Nebraska.
Yeah, that's the pairing that seems to take the longest. But which is there a single one that is? What's the most unique single entry? Yeah, Alaska. So here Alaska has this long stick that goes and goes and goes until it combines right here. And none of the others go that long by themselves. So yeah, who knows what they're plotting.
Bears.
What's that?
Bears.
Is pears?
Sorry.
Oh. Yeah. Do they grow pears? Is that what
Bears.
Yeah,
Bears.
Bears. Okay, yeah, that's right. I thought pears. I was like, I don't know anything about pears. Maybe they could grow pears in New Hampshire. Anyway, this is a great comedy hour here. Yeah. Anyway, that's fun. Let's do a Kahoot.